Hi everybody, in this video we are going to do Algebra 2 Q1 function transformation rules. But before we do that, we need to first just talk about a little bit what happens to functions when we do certain things to them. So over here we have a coordinate grid. We have an x-axis, a y-axis. You've seen pictures like this a million times. So along the x-axis, we have some numbers, 0, 1, 2, 3, 4, etc., -1, -2, -3, and so on. And what we're going to do is we're going to take each number on the x-axis and we're going to put it into this machine over here. So let's play pretend a little bit. We have this machine, this function machine, which takes a number, and what you do is you put the number in here and then the machine cranks it up and then spits a number out. Okay? So for example, if we put in the number 3, if we put the number 3 in here, then the machine would do whatever it does, and then it's going to spit out the number 2. You can see that if we put 3 in, then we get 2 out. If we were to put in the number, let's say 1, then out comes the number 3. Okay, and so forth. We've done functions before. But what happens if we take a number from the x-axis and then put it into the function machine, and then we add 2 to the result of whatever the function machine gives us? Well, it's actually not too hard to see what's going to happen. So if we put in the number 1, then again, we know from before that the function machine is going to give us the number 3. Okay? But then if we take that 3 and then we add 2 to it, we would get 5. Okay? What happens if we put the number 3 into the function machine? Well, the function machine we know from before is going to give us the number 2 out. But then if we add 2 to that, we would get 4. Okay, and we can do some more examples. Over here, from this graph, we know that if we put -6 into the machine, then it would give us 0 out. We can see that this is right on the x-axis here, so the y value is 0. So if we put -6 into the function machine and get 0 out, and then add 2, then we would get 2. 0 plus 2 is 2. So in that way, we can just figure out where all these dots should be. Here, if we put -3 in, then we would get -2 out, but then if we add 2, then we would get 0. Okay, and we can just keep doing things in that way, and this is going to end up looking like this. Okay, it's going to be exactly the same as before, except 2 spaces higher. All right? Now, if we had, instead of added 2 to the end, if we had subtracted 2, then you probably can figure out what it would look like. It would look exactly the same again, but everything would be 2 spaces lower from where it was before. So it would have been translated down by 2. Okay, so for example, if we put in the number, let's do, what's a good number to put in? If we had put in the number -4 into the function machine, I know from over here, when I put -4 in, I should get the number 1 out. So if I put the number -4 into the function machine, I'm going to get 1 out. But then if I subtract 2 from that, I would get -1, because 1 minus 2 is -1. Okay, and we could keep doing that with all the numbers. And in the end, we're just going to see that everything is 2 spaces less than where it was before. So everything has been translated 2 spaces down from where it was over here, okay, going from here to here. Okay, so this is not too hard. If we have some function and then we just add something to it, then all that does is it translates the graph of the function up by however many spaces we're adding. If we subtract something from it, then it would just translate it down by however many spaces, by however much we subtracted. Okay, so hopefully that's not too difficult to understand. Now let's do something a little bit trickier. Now, remember before we did the function, so we took our x value and we plugged it into the function, and then we added 2 to the result, okay? Now what if we do this? What does this mean? Now if we have that plus 2 inside the parentheses, let me just write this a little bit cleaner. This is not the same as what we just did. Now what we're doing is we're taking the number from the x-axis and we're adding 2 to it before plugging it into the function machine. We are going to start changing the numbers before we put them into the function machine, but we can always refer back to this graph as our record of what happens when we put certain numbers into the function machine. So let me explain what I mean by that. Over here, if x is 4, 4 is not the number that I'm putting into the function machine, because first over here we're going to add 2 to the 4 and we would get 6. So actually 6 would be the number that we put into the function machine. Now, how do we know what is going to come out of the function machine if we put the number 6 in? Well, we can refer back to this graph over here, because back in this graph, when the x was 6, then we put that 6 directly into the function machine. And we saw that we got the number 2 out. So this graph, since x was not changed at all before being put into the function machine, this graph is sort of a record of what you get as your output for every input that you put in. All right. So let's see what happens here. So for example, what if I took the number 1? So what if x is 1? All right, I'm not going to take this 1 and plug it directly into the function machine. What I'm going to do is I'm going to add 2 to the function to x first, and then put that number into the function machine. So 1 plus 2 is 3. So I'm actually going to put the number 3 into the function machine and see what comes out of it. Now I know from this graph over here that if I put 3 into the function machine, then I'm going to get 2 as a result. So that's how I'm going to graph it over here. Let's do a few more examples and see if we can see what's going on here. All right, what if we put, let's say, the number -1 into the function machine? Sorry, what if x is -1? So that means that we're not putting -1 into the function machine. We're taking -1, we're adding 2 to it, and then whatever number we get, that's what we're going to put into the function machine. So -1 plus 2 is +1. -1 plus 2 is positive 1. So we're putting positive 1 into the function machine. And now let's see what we get out. So going back to this graph, if we know that if we put 1 into the function machine, then we get 3 out. Okay, so graph is going to look like this. What if we put what if x, I keep saying put into the function machine, that's not what I mean to say. What if x is -5, let's say? If our x value is -5, does that mean that we're going to put -5 into the function machine? No. First, we're going to add 2 to it, and then we're going to put that into the function machine. So -5 plus 2 is -3. So we're actually going to be putting -3 into the function machine and seeing what we get out. So this graph over here tells us what would happen if we put -3 into the function machine. And according to this graph, the function machine would give us -2 out. Okay, so if our x is -5, and then we add 2 to it, we would get -3. If we put -3 into the function machine, we would get -2 out. So over here, we're going to put a dot at -2. Okay, now if you keep doing this for more points, then eventually you would see that this graph would look like this. Okay, so what happened there? The graph didn't go up and it didn't go down. What happened was it moved to the left. And that might seem strange. I know if you see +2, you might have thought that it should move to the right. And honestly, this is something that I got confused about myself so often when I was a student. I would see +2 and I would think, okay, it's gonna go to the right. But actually, if you see plus here, if you're adding some positive number, then it would move to the left. Okay, so for example, this bump over here was moved 2 spaces to the left. Now it's over here. Okay, this bump over here was also moved 2 spaces to the left. Now it's over here. All right, this bump, which used to be above -4, now on this graph, it's above -6. So everything over here was moved 2 spaces to the left when we add 2 to the argument. And the way that I like to think of that intuitively in my mind now is I always make the analogy with time. And I think of somebody who is maybe completing a project and they do everything maybe 2 minutes ahead of somebody else. So for example, after 1 minute goes by, then this guy is already where this guy is going to be at 3 minutes. He got there earlier. Okay, so after 1 minute goes by, then this guy is here. That's where this guy is going to be at 3 minutes. Okay, so if we add 2 to the argument, it's like we're saying, okay, I'm going to get to where you're going to be 2 minutes from now. I'm already there. Okay, so hopefully, so that's why everything here is moved to the left. It's sort of like he's doing things earlier than the other guy. He's doing now what the other guy is going to do 2 minutes from now, after 2 more minutes pass. Okay, now what would happen if we change this +2 to a -2? Well, you probably can guess what's going to happen. We'll do a couple of examples. So let's say that let's say that x is 3. Then if we put the 3 in here, we get 3 minus 2, which is 1. So we're putting the number 1 into the function machine. And then we can look back at this graph and we can see, okay, when we put the number 1 into the function machine, we should get 3 out. So back over here, when our x was 3, 3 minus 2 is 1, we get 3 out. So when x is 3 over here, we would get 3 out. Okay. Let's do another example. How about if x is 5? If x is 5, and we put 5 in for x here, 5 minus 2 is 3. So we're putting 3 into the function machine, and we know from this graph that when we put 3 into the function machine, we would get 2 out. Okay, so we're going to put a 2 over here. All right, and again, you can continue playing around with more numbers, and what you're going to see is that this is what it would look like in the end, even though I'm not doing a very good job of drawing it. Okay, so it didn't get higher or lower. Okay, the maximum value here is 3, just like it was back here. The minimum value over here is -2, just like the minimum value over here is -2. So the graph didn't get any higher or lower. What happened was it was shifted 2 spaces to the right. All right, so if this is -2 here in the argument, then it's going to the graph gets shifted 2 spaces to the right. So for example, this bump over here, which was at 1, now it's over here at 3. This bump, which was at -4, now it's over here at -2, right? At least on the x-axis at -2. Okay, so everything moved 2 spaces to the right. And why is that happening? Again, I like to use the analogy of time. So now this guy is always where this guy was 2 minutes ago. So at let's say the 3-minute mark, this guy managed to get here, but this guy was already there at the 1-minute mark. Okay, so again, this guy is now where this guy was 2 minutes before. So he's running late, in other words, and that's why everything here has been shifted to the right. Okay, now what happens if we take the opposite of f of x? This, by the way, is pronounced f of x, as in a function of x. So notice that here, the argument is simply x, like it is over here. So we're taking whatever is on the x-axis, and we're plugging that directly into the function machine and seeing what we get out. But then after we get our output, we're going to take the opposite of it. Okay, so what would happen? If x is 1, then we put 1 directly into the function machine. And we know from this graph that if we put 1 directly into the function machine, we get 3 out. Okay, so this would be 3, but then we're going to take the opposite of that. So we're going to put -3. What if we put, how about -4? What if our x is -4? So we put -4 directly into the function machine. Okay, so it's a function of x. Okay, we're not doing anything to x in this argument. We know from this graph that if we put -4 directly into the function machine, we would get 1 as our output. Okay, but we're going to take the opposite of that, so we would get -1. Opposite because of this negative symbol over here. Now, having a negative symbol here does not necessarily mean that we're always going to put a negative number down. So for example, if our x value is -3, so we put -3 directly into the function machine, we know from here that if we do that, we would get -2 out, but then we would take the opposite of -2. So this would be like the opposite of -2, which is +2. So we would have to put a +2 over here. Okay, so again, if you do that with all the numbers over here on the x-axis, and you refer back to this graph to see what would happen if you put that number into the function machine, and then you take the opposite of that number, what would happen is that everything would just flip. Everything that was positive before would become negative. Everything that was negative before would become positive. So our graph would end up looking like this. Ooh, let's see if I can do this or if I confuse myself. All right, and then let's see. This line was at +2 over here, so now it's going to be at -2, right? So I'm going to move this over here and then start drawing this way. Okay, so everything. Whoa, not what I meant to do. Okay, you can see everything got flipped, right? So this used to be here, now it's up here, okay? This used to be here, now it's down here. Everything just got flipped over. Yeah, so that's it. Well, I should mention that it was flipped vertically. It was flipped in the up and down direction, okay? Now let's see what happens if we do this. This is not the same as what we just did. Now, we're not taking the x value and putting it directly into the function machine. Now what we're doing is we're taking the opposite of that x value and putting that into the function machine. So for example, if x is -1, then this would be the opposite of -1. Whoops. The opposite of -1. I have to write 2 of these over here, which is +1. So I'm actually putting +1 into the function machine. And I know from this graph that if I do that, I'm going to get 3 out. Okay, now let's see. What would happen if our x was 3, then this would be the opposite of 3. So we're putting -3 into the function machine. And we know from over here that if we put -3 into the function machine, we would get -2 out. So this should be -2. Okay, what if our x was 4? Then we would actually be putting -4 into the function machine. And we know from this graph that we would get +1 out. Okay, so can you see what's going on here? So if you were to continue doing this with every number on the x-axis, this is what it would look like in the end. Again, the graph is flipped, but instead of being flipped vertically, it got flipped horizontally. Why did that happen? Because for example, when x was 4, we didn't put 4 into the function machine, we'd put -4 into the function machine. So we got over here the same thing that was on this graph, but over here at -4. And when we put -4, when x is -4, then instead of putting -4 into the function machine, we would have put +4 into the function machine. And then we would have gotten back over here what the result was over here when we put +4 in. Okay, which was 2. Right? So that's why everything is getting flipped horizontally. All right. What else do we need to do? What happens? What if we were to do something like this? How about 2 times f of x? So again, we're taking the x value, we're plugging it directly into the function machine, and then whatever we get as our output, we're going to multiply it by 2. So if our x is 1, then we put 1 into the function machine, we get 3 out, but then we double it, so we would put 6. If x is 3, we put 3 into the function machine, we get 2 out, but then we double it, we get 4. Okay? If x is, let's say, 6, then we know from here that if we put 6 into the function machine, we would get 2 out. But then if we double it, that would be 4 again. And this is, what about, let's try -6. If x is -6, then we put that directly into the function machine, and we know from here that we would get 0, and then we double that, it would still be 0. So this point would stay there. Okay, so in the end, this is going to look like this. This down here, it was at -2. If we double that, it'll go down to -4, right? And then back up here. Okay, so it'll look like that. Everything is going to get stretched out in the vertical direction. All right, and you can see that everything is twice as high or twice as low as it was over here. So hopefully that's not too hard to see. Nothing happened horizontally. All the stretching was done vertically. Now, what if we had put a half instead of 2? Again, all of the stretching would be vertical, but it wouldn't really be stretching, it would be shrinking. Everything would become half as high, right? Or half as low. The zeros would still stay where they were. But then, so for example, instead of here going up to 1, this would only go up to a half. Instead of going down to -2, this would only reach down to -1. Let's see, instead of going up to 3 like it did over here, right? If our x value is 1, we put 1 into the function machine, we get 3 out. So this would become 3, but then 3 times a half is 1.5. So this is only going to get up to half as high as it did before back over here. All right, and then let's see, this is going to go back down to 1 over here. So again, there's sort of the opposite of stretching. It's shrinking this way. If this coefficient over here is a number which is less than 1, then it's going to shrink. If this number is greater than 1, then it's going to stretch like that. I should say the absolute value, because technically, if I put in a number like -5, -5 is less than 1 technically, right? But -5 would actually, it would stretch it and also flip it. So I should say when the absolute value of the coefficient is greater than 1, it would stretch. If the absolute value of the coefficient is less than 1, then it would shrink. right? And then if it's if it happens to be a negative number, then it would also flip it. Okay, what else do we need to do? All right, so this is the last thing that we need to talk about. What if we had, instead of a 2 or a half on the outside here, what if we put it inside in the argument? Let's start with 2. All right, so let's say that... all right, let's say that x was a half, 0.5. So if x is a half, then we would have 2 times a half, which is 1. So actually, a half would not go into the function machine. 1 would go into the function machine, and we would get 3 out. So that's where we're going to draw the dot over there. If we put 1.5 into the function machine, if our x value was 1.5, then the number that we put into the function machine would be 3. And we know that if we put 3 into the function machine, we would get 2 out. So this would be 2 over here. Again, you could keep playing around with this, and what you're going to see is that even though the absolute value... hang on, you know what? I can't talk and draw this at the same time, actually. This takes a little bit of concentration, so hang on one second. This should go 1.5, -1. Okay. And then up like this. And then let's see. Okay. All right, so let's see if we understand what happened, let's say, over here. So the x was -2. So if we do 2 times -2, then we would actually be putting -4 into the function machine. And we know that if we do that, we would get 1 out. So over here at -2, this goes up to a y value of 1. Okay. So actually, by putting a coefficient inside the argument, which has an absolute value which is greater than 1, instead of stretching, it would be shrinking. And it would be shrinking along the x-axis. Okay? And, just to get an intuitive sense of why that's happening, again, I like to think of time. So everything here is kind of happening twice as fast, right? So when 1 minute passes, let's say this guy's twice as fast as this guy over here. By the time 3 minutes went by, this guy went up here and then down here. Meanwhile, this guy who's twice as fast, he managed to go up and down and it only took him 1.5 minutes. All right. So the 2 is like he's going twice as fast, so he accomplishes everything in half the time. I also used the time analogy earlier in the video when we were talking about something like this. You know what? Let me just draw another grid. Okay, so let's say we already did this, but let's say something like function of x plus 2. Then what did the graph look like? If you remember, it was like this. Oops. Okay, so I'm not doing a very great job of drawing that. But the point is that this one is scrunched like that. Meanwhile, this one is not. So here you can think of the guy going twice as fast. So he accomplishes everything in half the time. Here, he's not going twice as fast. He's just getting everything done 2 minutes earlier. So it still takes him the same amount of time to do it. He just was finished with everything earlier than this guy over here. All right, but it's taking him the same amount of time. So the length from here to here, say, is the same as on this graph as the length from here to here. It just finished earlier. Okay, so you have to be careful when you're using that time analogy, like I like to do. For something like this guy is doing everything 2 minutes early, but it takes him the same amount of time. This guy, he's doing everything twice as fast. So that's why he's sort of going up and down faster than these guys over here. Okay? The last one that we need to talk about is what happens if instead of having a half out here like we had before, we have the half in here. Then this guy would be going half as fast as this guy over here. So it's going to take him twice as long to finish everything in the analogy that I was using a moment ago. What that's going to do to the graph is it's going to stretch everything out horizontally along the x direction. So let's see. So here, instead of reaching that high point at 1, this guy's going half as fast. He's going to reach that point at 2. And then down here at -3, I know the analogy kind of breaks down if we're thinking about negative time. What does that mean? But anyway, this low point would be reached at -6 instead of -3, right? Okay, so the graph, and then the rest of it would be off the graph. So I'm not going to draw this part over here. Let's see, this point was at 3. Now it's going to be at 6. Okay, so something like that. So this guy is going half as fast as this guy over here. So it takes him longer to finish everything. That's the analogy that I like to use. But let's just make sure that all of this is actually correct. So if the x value is 6, then we would get a half times 6, which is 3. So we would be putting 3 into the function machine, and we would be getting 2 out. Okay, which is what we have over here. Okay, so I hope that I drew that correctly. I think I did. All right. So yeah, it would get stretched out in the horizontal direction. Now we can actually go over to IXL and do some IXL problems. Now we have all the knowledge that we need, all the understanding that we need. Where's IXL? Over here. Okay. What does the transformation f of x to f of x minus 9 do to the graph of f of x? If we see this minus 9 outside, then that's going to translate everything down 9 spaces. Okay. Okay, here again, we're plugging the x values directly into the function machine and then just subtracting 1 from whatever we get from the result. So what's going to happen there, just like I think the second example that I did in this video, everything is just going to move down. It's going to get translated down 1 by 1 unit. Okay. Here, notice that this plus 10 is inside the parentheses. So So we're adding 10 to x before we put it into the function machine. That's like the guy who's doing everything 10 minutes early. So maybe he started something at 3 o'clock that the other guy only started at 3:10, and he finished whatever project that was, let's say at 5 o'clock, and the other guy finished the project at 5:10. So everything for him is done 10 minutes earlier. All right, that's going to translate everything to the left. He's getting everything done earlier. It's going to translate everything to the left by 10 units. Okay, here two things are happening. This -8 inside the argument is going to shift everything to the right by 8 units. And then this -5, which is outside of the argument, is going to shift everything down by 5 units. So here's something to remember. If you see a plus or a minus inside the argument, then it's like the opposite. So we saw a -8 here, but we didn't shift in the negative direction. We shifted in the positive direction. If I see a -8, if I see a minus sign inside the argument, I'm going to shift in the positive direction, which on the x-axis is to the right. But if I see a minus sign on the outside, then I am actually going to shift in the negative direction and I'm going to go down. Okay? So everything is what you would expect it to be when this minus or plus is on the outside. But if it's on the inside, if it's inside the argument, then it's the opposite of what you might expect. Okay, so here with this -8 on the inside, that's actually going to shift it to the right 8 spaces. And this -5 on the outside is going to shift everything down 5 spaces. Let's see. So this one, okay. Oh, 8 units. What did I pick? Oh, whoops. I picked 5 units to the right. 8. Yeah, it's 8 units to the right and 5 units down. Yeah, so pay attention. Okay, that is what I was saying, but I clicked on the wrong one. All right, so over here, we see the -10 on the outside, which means that everything is going to be shifted down 10 spaces. Okay? We see the minus sign and everything is going down. So it is what you would expect. You got to be careful when you see it inside the argument, because then it's like the opposite of what you would expect. Okay. Okay, here I see a minus sign inside the argument. That's going to shift everything along the x-axis, but it's going to be the opposite of what I expect. So you might think -6, it should go to the left, but for -6 inside the argument, it's actually going to go to the right. So let's see, 6 units to the right. So it's either this one, which other one says 6 units to the right, or this one. Then this -1 on the outside, it's going to shift everything 1 unit down. Okay, so that one. Okay, +10 inside the argument is going to shift everything to the left 10 spaces. -6 outside the argument is going to shift everything down 6 spaces. Let's see, 10 units to the left, 6 units down. All right, should I skip a level here? I'm going to skip ahead. Okay, this is like everything is happening twice as fast, right? And what that's going to do is it's going to shrink the graph along the x-axis. We just did that example a few minutes ago. All right, so it would shrink it horizontally. Remember, this is horizontal, this is vertical, right? Vertical is the up and down direction, horizontal is the left and right direction. Okay, here, it's like the guy is going 1/9 as fast. He's actually going slower. If you're going 1/9 as fast, then you're actually going slower than everybody else, right? So his graph is going to look lazier. It's going to take him 9 times longer to finish everything, which means that his graph is going to look stretched out in the horizontal direction. Okay, here notice that the that 1/6 is on the outside. That's not inside the argument like the last two examples. Rewind so you can see the difference between having a number on the outside and having a number on the inside. This fraction here, 1/6, is on the outside. So that means that this guy is going just as fast as everybody else, okay? So we're not going to shrink his graph this way, and we're not going to stretch it out this way either. He's going just as fast as everybody else, but then when we get the output, we have to multiply it by 1/6. So that's going to shrink it in the vertical direction. Notice something else which is important. When we have a number on the outside, which is, I can't highlight it. Okay. When we have a number on the outside, which is less than 1, okay, the absolute value is less than 1, that would shrink it. And if we had a number on the outside where the absolute value was greater than 1, that would stretch it. But it's the opposite when it's inside the argument. Inside the argument, if we had a number that was less than 1, that would stretch it in the horizontal direction. If we had a number which was greater than 1 inside the argument, then that would shrink it in the horizontal direction. Okay, but here we had a number less than 1 on the outside. That's going to shrink it vertically. You know, there are so many, you could just try to memorize all of those rules. If I have a number that's greater than 1 on the outside, it's going to stretch it vertically. If I have a number which is smaller than 1 on the inside, it's going to stretch it horizontally. But there are so many rules to remember. Really, the best way to do it is to make sure that you watched the beginning of this video and make sure that you understand everything. So instead of memorizing a million rules, you actually have some intuitive idea of what's going on. It's going to make doing this so much easier. Okay. All right, here, 9 times f of x. Okay, so all those x values are going straight into the function machine, but then everything is getting multiplied by 9. So that would make it 9 times taller and 9 times lower. So it's going to stretch it vertically. All right, let's go ahead. Oh, now we're getting some reflections over here. Yeah, I said instead of using the word reflect, I used the word flip, okay? But we did actually talk about this, except that's not even one of the answers for this one. So this is just going to stretch it vertically. We did a problem just like that before. Okay. Oh, I'm on the last level already. So you know what? I'll just end by talking about if you get one that says reflect. I didn't use the word reflect when I was doing these examples over here. I used the word flip, but if you have something like, we did this example already. If we have a negative inside the argument, then that would flip it this way. Let's see. Oh boy. That's a negative. Okay. Okay. So if we see a... No, I'm sorry. Whoopsie daisy. That should be... No, I'm sorry. I apologize. That should be outside. If I see a negative outside the argument like that, then that would flip it vertically, okay, which would also be called a reflection over the x-axis, okay, because it's like we took this and we just reflected everything over the x-axis to get this, okay? That's if we see a negative on the outside. If we see a negative on the inside, then this graph over here would look like, this now. Let's see. Yes, and then that. Oof, this is tough to do. Okay. This, and then that, and then that. Okay. So if we see the, and we talked about this earlier in the video. So if we see the negative on the inside, then it would flip everything horizontally, and that would be a reflection. That would be, well, really, here's where we started. So that would be a reflection over the y-axis. Okay, so this would go over to here. This would go over to here. Okay, all right. So it looks like I'm on the last level of the exercise already, and we've already done problems like this. So I'm going to end the video there, and have a great day.